Okay, in this session we are going to now look at the Charles law, and what we will also do is first understand the Charles law and the relationship, and then we are going to look at a simulation using molecular dynamics lab. So, Charles law essentially says that if I take again, let us take two systems. We have one system here and we are going to do constant pressure. So, the pressure is right here. So, this is same weight and we are going to heating it up here with a lamp, and this situation is state 1 is T1 and V1 is constant. So, now we go to T2 where because we are giving more temperature to the system through this flame out here, then as the T2 goes up, the V2 also goes up. So, what it says is that the volume is proportional to temperature. And so, if I look at these two situations, then proportionality says to me is V1 over T1 is equal to V2 over T2. So, if we just do simple multiplication, then V1 multiplied by T2 is equal to V2 multiplied by T1, and that is the Charles law that we want to establish with our experiment in the molecular dynamics. So, now let us go to the molecular dynamics experiment on our VMDL and see if that actually is true based on our simple calculations. So, let me expand this. Make that bigger. We are going to show the averages. Let's make this full screen. Now, we are going to go and look at temperature. Pressure is going to be constant. So, let us look at temperature versus time in this case as compared to what we did in the Boyle's law. So, now if you look at here, we are going to run some steps. So, again this is a moving boundary, but constant pressure, because in the Charles law the quantity which is constant is the pressure. So, now if you start here, which says you have 200 particles under the piston, gas is kept under constant external pressure. What is the temperature graph as we go through it? So, let me also look at the real units and put them on the side. Let us move forward. Now, we went through some steps about 3.89 seconds with 300 particles using molecular dynamics simulation of this situation. Now, you can look at the temperature is around 2. Now, we go further up. Second step, now you saw the temperature going down. As the temperature goes down, you can also see the volume going down. Let me go back, rewind it a little bit back. So, we are starting with a certain volume. So, I am going to take it again, and that volume is 2.86, I believe. Now, we are going to further reduce the temperature. Let the temperature go down. Now, we are going to see that the temperature is gone to about 1.7. Let us go further down. So, here is the temperature going further down, and you can see the volume going down as well with the temperature. Now, we are all the way down to temperature 1.2, and we are seeing volume as going from 2.66. So, starting from about 3, now we have gone to 2.41. So, now what I would suggest to you that using this tool that you have in front of you, where you also can simulate, there is also a simulation for this kind of situation. So, you can now look at the temperature versus volume graph, and if you take 3 different temperatures and then you calculate the volume changes, then you should be able to plot the line between temperature and volume, and that should be a straight line increasing between the volume and temperature. So, So, let us rewind it one more time and see the whole process happening in front of you. So, now you can see from lower temperature you went to the higher temperature. So, we start with the higher temperature, time 1.0, temperature is 1.99, we reduce temperature to 1.9291. So, temperature has gone to 1.71, volume is in real units is temperature. Let's look at 204 Kelvin temperature and the volume is 2.75. For the reduction in the temperature, gone to 198. Let's go further down. So, we gone to 181 and the volume gone down to 2.41 meter cube. So, that explains how the Charles law works. So, if we go back and so now let us go back to our slides. So, I want to show you the relationship there and let's go back to the original size. So, here is a very crude animation that you can look at for this situation, and you can now see the straight line emerging out of the pressure, volume and temperature relationship. From this understanding, now we are ready to look at phase transitions of different kind between temperature and volume space. And as you can see that with 5 different locations we can look at different volume and temperature relationship. However, now we can also look at the constant pressure phase change process. So, now we are increasing the pressure on the system. So, now this diagram that you have, which is between temperature and volume, but at different pressure lines. So, these are called isobars. Isobar means a particular thermodynamic process with a particular pressure. So, first we look at pressure 0.01 megapascals, and we then observe the phase changes from between temperature and volume of a substance, and this is a pure substance. Then you go to 0.1 megapascal, which is 10 order of magnitude. Then we go another 10 order of magnitude multiplied by 10, 1 megapascal, and this is how we are looking at. So, if you look at this point, this is the critical point. So, if you look at here, the saturated liquid is on this side and it's still liquid, but at this point now it is going into the vapor phase. So, this point at which the pressure is now at the critical level, that is where we call it critical point on the pressure diagram. So, now we are understanding between pressure, volume and temperature. So, if you look at, we now have looked at 3 relationships. The Boyle's law gives us relationship between pressure and volume. It says multiplication of pressure and volume is constant. If you look at the Avogadro's laws, it says that the number of moles of the gas is constant in a given volume. So, V over N is a constant. And then the Charles law says that the ratio of volume and the temperature is constant. So, now we have these 3 laws that we are looking at. So, now we will think about how we combine it together to create a universal gas law, and that again we will try to look at through molecular dynamics simulation to see whether we can take small number of particles and create those situations. So, I think by this time I am sure you know, and I am repeating myself many times, but that is the power of computational engineering and science, is that a real physical situation can be simulated by few hundred particles, in this case 200 particles that we are using here. Thank you.